Good afternoon. It's a beautiful sunny Friday. I get lots of sunshine out there and people walking around in warm weather, and I'm going to record a lecture because that's how I roll. Okay, in the previous recordings, I talked about the various properties of thermodynamics, the movement of energy. And in the most recent recordings I did for you, I talked about the concept of temperature, first of all, and I said that temperature is a number that we assign to a system, and it takes the place of trying to calculate how much energy, how much thermal energy a system contains. And so, and in a later lecture, and I keep promising this, that it'll happen eventually, I will show you the actual mathematical relationship between the thermal energy of a system and the temperature of that system. But in any case, the point right now is that the temperature, pardon me, is it takes the place of trying to calculate the internal energy, which we can't do even in principle. So in practice, we have the same information, we obtain the same information from just the concept of the temperature of a system. And I talked about the two of the three laws of thermodynamics. The zeroth law, I said, so if you have three systems, I labeled them A, B, and C, and I said that if system A and system B are in thermal equilibrium, and if system B and system C are also in thermal equilibrium, then the zeroth law says that systems A and C must therefore also be in thermal equilibrium with each other. So if A is in equilibrium with B, B is in equilibrium with C, then A is in equilibrium with C. And then the first law of thermodynamics discusses how to change the thermal energy of a system. And there's two ways to do it. You can either do work on the system, force through a distance, right? Do something to push the particles that make up that system around through some force that pushes them through some displacement. That'll do work on them, and that will increase the thermal energy. The other way to do it is to transfer energy, in other words, to have some heat flow from one system into another system. And so the addition of that heat would also increase the thermal energy of the system. And the first law says that the change in the thermal energy of the system is the sum of those two things, the sum of the work that you do in the system plus the heat that you transfer into the system. So, the zeroth law, let's see, we can go over here. A is in equilibrium with B, and B is in equilibrium with C, then A is in equilibrium with C. That's the zeroth law. And the first law says that the change in the thermal energy of a system is simply the sum of the work that you do on the system plus the amount of heat that you transfer into the system. Okay. And I said that there are three laws. So let's talk about the third law, which of course is actually just called the second law. I think I said in the previous video the reason for the zeroth law, rather than calling it the first law, is that the first and second laws were stated first, and it wasn't until after they had been stated and accepted and people worked with them for a long time that it was pointed out that this unspoken assumption was being made, and that was fundamental to the first and to the second law, and it had primary position conceptually above them both, and so that got inserted that way. Okay, so the second law of thermodynamics then is the topic for this recording. And to explain that, I want to take a look at an ice cube and at a glass of water. So let's start out with a glass of water. Now, from a macroscopic view, of course, I might just color this all sort of a mostly solid blue, and that would represent the water, and we would think of it as a fluid, as we typically do. But for my present purposes, I want to examine the water as a collection of water molecules. And so this is the surface of my water there. Then the water filling this glass, bunch of H2O molecules, which I'll just represent with dots here. And this glass of water, being made up of individual particles, H2O molecules, has some thermal energy, which is just another way of saying that it has a temperature. Of course it has a temperature, and in fact its temperature has got to be above the freezing point of water, which at sea level anyway, under ordinary conditions, is about 0 degrees Celsius, or 273 Kelvin. Have I talked to you about the Kelvin scale yet? I'm not sure I have, but whatever. Anyway, this is above freezing is all that I need you to care about right now. Since its temperature is above 0, above freezing, then the system has a certain amount of thermal energy, which means that all of the individual water molecules are in motion. They all have kinetic energy. That's what thermal energy means. Okay, so they're all moving around in lots of directions. And so this one here is moving that way until it collides with this water molecule, then it moves this way, then it collides with this one, moves this way, collides, moves that way, this way, this way. And in fact, as time goes on, just this one particle will skitter all around the entire volume of this glass of water. Okay, and so if I were to look at it, and if I could somehow take a photograph of all of the particles of water, if my camera could zoom in that tightly, and I could see individual water molecules, then if I took a picture of it, and then I'd have a picture and it would show all these particles, and then if I took a second photograph a moment later, if I could somehow tell the water molecules apart, then what I would notice in my second picture is that every one of the water molecules has changed position. I still have overall a glass of water, but the locations of each individual water molecule has changed from one photograph to the next, to the next, to the next, to the next, to the next. And there are, of course, this being three-dimensional and the glass of water being huge compared to the size of an individual water molecule, that means that there are uncountable trillions of possible sets of possible positions for every one of these molecules. In other words, at one instant, this one molecule is here, the next instant it's here, then this one here, and this one. And that's true of all of the particles, of the quadrillions of water molecules that make up this ordinary glass of water. And this thing is three-dimensional, and they'll move in up, down, front, back, left, right? And so there's, like I said, the number of possible combinations of positions for every one of these molecules is huge. And we don't even try to count them. We don't even try to think about them. Okay? However, I am bringing this up for a point, though. Even though we don't talk about them or think about them or, God help us, try to calculate them, there is something, there is some useful information here, nevertheless. Especially when I compare this to the same glass of water. So let me say here that this is liquid. So the terminology is it's in its liquid phase. So then I take and I put this glass of water in a freezer, and I leave it there for a few hours or a couple of days or something, and pull it out, or leave it in the freezer anyway, looking at it. What I would find is the molecules, two things have happened. H2O molecules being of having the, let me say it like this, water molecules having the electric nature that they have, in other words, sorry, hang on. A water molecule, as you know, H2O, it has two positive charges. I'm sorry, it has the negative 2 oxygen and then the 2 positive charges of the 2 hydrogens, and so it has a particular shape. And when you make the system cold, what has happened is you cause the particles to move less. They have less kinetic energy. Okay, so they tend to not move very much at all. You might think they don't. You might think their motion is zero, but that's not true at all. They definitely still have some internal energy, but they have a lot less here than they did in the liquid phase. And in fact, here this is the solid phase. So this is just ice now. Okay, so they are still moving, but they're just moving a lot less than they do when the same water was in the liquid phase. Okay, so there's that, first of all. And so essentially the idea is that as the water cools down, the system loses thermal energy. And that means that the kinetic energy of the individual particles gets smaller. That means the velocities of the particles get much smaller. And as a practical matter, the molecules tend to line up in a more or less orderly, more or less crystalline array. That is to say, a nice ordered array forming crystals. And then as long as the temperature stays low, meaning the kinetic energy stays low, then this arrangement tends to stay the way it is, nice and stable. And in stark contrast to the liquid phase, if I were to take a photograph of the positions of the individual water molecules in the solid state, and then take another photograph a moment later and compare the two photographs, I would find that they are virtually identical. The particles have not changed position as they did in the liquid phase. Okay, so why am I telling you all of this? The fact is that the temperature of the temperature of a system is a useful number. It tells you something important about the state of the system, specifically how much internal energy it has, which from that you can determine all sorts of other things, and we'll be talking about some of those things in days to come, in recordings to come. But the temperature does not tell you everything that there is to know about it. And it is clear, I hope, that there's something significantly different between this system and this system, even though they're both the same water molecules with the same volume and so on. But clearly, these things are ordered, and these things are highly disordered. And this order here stays the way it is for long amounts of time. This, whatever the particular arrangement of molecules happens to be here, it stays in that same arrangement for tiny fractions of nanoseconds. Okay, so this is continuously changing. This arrangement essentially never changes, and so this seems like something at least useful to know about the system. And in fact, we give this idea a name, and the name is inspired by one way of describing all of this more succinctly, is I would simply say this system is more disordered or more random than this system. Okay, so this is, and the usual term is disordered. So I would say this is highly disordered. Disordered, very random, if you will. Okay. This one is small disorder, a small amount of disorder. Hardly random. But we have a nice, cool technical term for all of this. The the measure of randomness, the measure of disorder in the system. The technical term for that is called entropy. Unfortunately, I'm sorry, I don't know the derivation of this. I assume it's Latin for random or disordered. So the entropy of a system then is yet another property of the system, like its mass, like its temperature, like its volume, like its pressure. It's one of the variables that helps describe in full what our system looks like and how it's acting. The short version of that is this is one of the variables that fully describes the state of the system. Okay, so it's one example of what's called a state variable. The state variables are the most common ones are pressure, volume, temperature, entropy, a couple others. So entropy then is a measure of the amount of randomness, the amount of disorder in the system. So this system has a lot of entropy or has high entropy. The system has low entropy. Okay, so let me write that all down. Okay, so that's what entropy means. And it does have a number, and in subsequent recordings I will talk about that, but for right now I just want to get you a feel for what this word means and what it is measuring for us. There's another way to think about entropy. How do I know if entropy is large or small in any quantitative sense? It goes like this, basically. I mentioned a few moments ago that the possible arrangement of the possible number of arrangements of the particles that make up the liquid glass of water is vast, huge number of possible arrangements. In other words, suppose just to take a trivial example, suppose this thing were made up of 100 water molecules rather than hundreds of trillions. Okay, well. And suppose I said, okay, 100 of them, and then at some instant that I watched them, that I looked at this, water molecule number 1 was here, water molecule number 2 was here, number 3 was here, 4, 5, 6, 7, number 99 was here, number 100 was down there. Okay, and so that set of locations of where those water molecules are is one possible arrangement of those molecules. But as I was just discussing, the next instant, all of those positions will have changed. And so now 100 will be up here, and number 1 will be here, number 17 will be there, and number 62 will be up there, and so on. And they'll all get rearranged in the next instant. So that's another possible arrangement. And in the next instant, there's a third possible arrangement. In the next instant, a fourth. And again, even with just 100 possible, just 100 water molecules, there's a vast number of possible arrangements that the system could take on. And so out of all the possibilities, we only see one at this instant, and then we'll see another one in the next instant. Whereas contrasted with this system here has one arrangement of these molecules which is possible. That's stating it a little excessively, and I'll talk about that in the next recording. But in any case, essentially just one arrangement of these molecules, okay? And so in that sense, because they're frozen in place, right? And so that is in that sense that I say that this has a low entropy, a low amount of randomness. Another way to think about entropy is a measure of how many possible arrangements of the particles the system has. And the fewer possible arrangements that a system has, or that a system will take on as you look at it, as you watch it, the fewer number of possible arrangements there are, the lower the entropy is. Okay, so anytime I look at this, it's a very high probability that the water molecules will still be in the same frozen place that they were when I looked at it 5 minutes ago. Here, the probability that the particles will be in the same place, or at least have the same arrangement as they had 5 minutes ago, is essentially zero. Is just flatly zero. Okay. So high entropy, very low entropy. Not zero, by the way. This is definitely not zero entropy, but it's pretty low. Okay. So that's the idea. And so finally, the second law of thermodynamics has something to say about entropy. And actually, I think this is a good breaking point because at the beginning of the next recording, I'll tell you what the second law of thermodynamics says, and I'll bet you can guess it has something to do with entropy.